Once again, welcome to A-Level Physics, Cambridge A-Level. Today's topic is 3.2, non-uniform motion. Right? Let's go to the syllabus of Cambridge so that we know how far we need to cover. Show a qualitative understanding of frictional forces and viscous or drag forces, including air resistance. No treatment of coefficient of friction and viscosity is required, and a simple model of drag force increasing with speed increases is sufficient. As speed increases is sufficient. Describe and explain qualitatively the motion of object in uniform gravitational field with air resistance. Understand that object moving against resistive force may reach terminal velocity, terminal or constant velocity. Okay, so far we have studied about different type of motion. In particular, we study about uniform acceleration. So basically, in this topic, we are going to cover air resistance, where the air resistance will increase with velocity of the object. So in this case, the acceleration is normal, constant, or uniform. The acceleration decreases until it's zero. Okay, so there are some Facebook platform that you may want to visit. Physics AS, where I deposit my YouTube video here, my notes over here. This one is mainly AS past year paper before 2020 on PowerPoint. This one it will be also practical paper 3. Also, most of the papers before 2020. Okay, so this is uniform acceleration. Just to review with you: parabola, displacement time graph, velocity time graph, straight line, acceleration time graph, horizontal line, okay, constant acceleration. Okay, motion in viscous fluid. Free fall where air resistance is negligible. Negligible means air resistance is zero. That is the mass of the object. The only forces acting is the weight, mg. Mass of the object is m. Acceleration due to gravity is g. So the resultant force in this case is the weight, mg. Acceleration is downwards and is equals to g, constant. Right? If no air resistance, it's constant. Upthrust in air is negligible, as the density of air is very low compared to density of the mass. Viscous and terminal velocity. Viscous means presence of friction or resistive forces. That's forces that oppose motion. The key is oppose motion. So it means it tells you that the direction is always opposite to the direction of motion. Terminal velocity is the maximum constant velocity. This occurs when the weight is balanced by the drag. Drag is the resistive force that opposes motion in the fluid. Air resistance can be very useful. The push of the air on the parachute slows down the fall of the object. There's a person coming on the parachute, so its parachute slow down the object or the person. So the terms are quite similar: drag, air resistance, or friction, or viscous drag. Where you have a car moving on the road, then you have air resistance and friction. So these two together become the drag. Right? The key term is always remember direction of this force always oppose motion. This one, the object is moving downwards, so the drag is forcing it upwards. Motion in viscous fluid. But previously, we neglect air resistance. Now we want to understand what happened if air resistance is not negligible. We release the body from rest. Motion in viscous fluid, it can be liquid, can be water, can be air. Initially, when the ball is dropped, acceleration equals to g, because it's not moving yet. As the velocity increases, the drag forces F increases. As the drag forces is moving downwards there, the drag is opposing the motion. The speed increases, that F increases. So for low speed, drag force is proportional to speed. As the speed increases, drag forces increases. So we use Newton's second law to calculate our resultant force, F equals to ma. So resultant force mg is greater than F, so mg minus F equals to ma. So A equals to mg minus F divided by m. Right? So this basically tells us that as our speed increases, our friction increases, so that acceleration decreases. Right? So there will come a stage where friction or drag equals to your weight, then the acceleration is zero. So in this case, acceleration decreases with time. Okay, speed increases. At terminal velocity, it cannot increase anymore, right? The largest it can go for drag is where it goes to mg. After that, it cannot increase anymore. So weight equals to drag, acceleration equals zero. That means the body continues to move with constant velocity. This is what we call equilibrium. Okay, let's just summarize in the table. Initially, with the mass, the weight, right? There's a formula that we just derived. It has zero speed, so it has no friction, because friction depends on the speed. Acceleration is g. At any time t, before terminal velocity is reached, there's your weight acting, there's your friction acting, or drag acting, or air resistance. And the velocity as v increases, the friction or drag increases, right? F increases, so that decreases. At terminal velocity, the maximum or maximum or constant velocity, maximum constant velocity, your friction equals to mg. So in this case, the acceleration is zero. Okay, so these are the graphs that we are going to obtain. This is for uniform acceleration. This is non-uniform acceleration. The air resistance is considered. This is the velocity time graph for uniform velocity. No air resistance is a straight line passing through the origin. Uniform acceleration is this way, but with air resistance is going to decrease. Okay, so that's a parabola for dropping your object in air. Air resistance is negligible, or we call it free fall. Falling ball would be opposed by friction. This means that the acceleration will decrease. At each particular time, the distance traveled will be shorter and the speed will be smaller. Right? Same time, shorter distance because the speed becomes smaller and smaller. Then there will be a point where we call terminal velocity is reached. Right? So this line is presence of air, of friction or air resistance. When the ball has reached terminal velocity, the velocity would be constant. After that, it's constant velocity, terminal velocity, so it's a straight line. Right? For this part onwards, straight line, where it reach terminal velocity. Right? Velocity time graph, no, or non-air resistant, is a straight line passing through the origin. Right? Remember, terminal velocity is the maximum constant velocity. For a small distance, the speed is slow, friction is negligible, and the curve is the same as the free fall. Right? So at this part there, it will be the same. As friction increases with speed of the ball, at the same time, the speed would be increasing by smaller amount. The speed will decrease again already because of air resistance speed. For low speed, it's almost a straight line. After that, it goes further and further away because the speed decreases. And near terminal velocity, it's almost horizontal. So this line is the presence of friction or air resistance. The net acceleration at any time will decrease with increasing speed. Friction increases at any time. Acceleration decreases at any speed. So that is terminal velocity, horizontal line here. At terminal velocity, the acceleration is 0. Okay, which is the acceleration time graph for motion in the viscous fluid? Okay, you guessed correctly. Donkey, D. This one is uniform acceleration. Right, so we just summarize what we have learned. Velocity and acceleration time graph. How would the acceleration time graph looks like? This is a velocity time graph where air resistance is not negligible. This is for uniform acceleration, taking downwards as positive. So acceleration decreases to 0. Right? The air resistance is not negligible. Then we can roughly decide if we are given a graph there, we can break up into small sections. The smaller the better. To sketch the acceleration time graph, break the curve into straight line, right? To different interval of time, like that. Right? Make it approximate with a straight line. So if it's a straight line, velocity time graph gives acceleration. So this is steep slope, the high acceleration. Is smaller slope, smaller acceleration. So we take the middle point and draw the graph. Right? So that's how we approximate roughly how the graph looks like. For higher velocity, where the fluid flow is likely to be turbulent and friction is proportional to velocity squared. This is where on the rainy season, if you look into the drain there, you see the water moving very fast. That's called turbulent. Right? Normal. At this time, the friction is proportional to the velocity of the object. You can observe terminal velocity for insect. 1 millimeter insect is 6. Round stone 24. Raindrop 8. Human is 50. Right? Human being heavier and larger. Human with parachute is 10 only. So for small object, terminal velocity is very small. For large object, example human is quite large. Increase the parachute, that means you increase the surface area to air resistant, so terminal velocity becomes smaller. Right? This experiment, usually for paper 5, question 1, right, we can use to study motion. or to investigate how the diameter of the ball bearing affects the terminal velocity, or to investigate how the velocity of the ball bearing changes with time in the viscous fluid, or to investigate the terminal velocity changes with temperature of the fluid. Right? Basically, it's not required for paper 1 or paper 2. Right? This is just for general knowledge. Right? We can have rubber band every 10 cm. There's your rubber band. There's your glycerin or motor oil. There's your red one is your rubber band. 10 cm apart. This is your long tube 1 meter long. Can be made of glass or made of plastic. Then we drop the ball bearing just below that. And note the time and distance travel every 10 seconds and tabular. Then draw the graph of distance time graph. And then at different time interval, we draw tangent to the curve to find the velocity time graph for each time. Right? And plot a graph velocity time graph. We caution this one must be wide compared to the diameter of this ball. Okay, let's go to try some question. Which of the graph represent sketch the graph to show how the weight of the body changes with time. Have a go. How the frictional force varies with time. How the velocity varies with time. How the resultant force varies with time. Weight is constant. Yeah, right? There is horizontal line. Doesn't change with time. Friction, how does it change with time? Same with velocity. Friction is proportional to velocity, so the graph is the same. How does the resultant force varies with time? Same as the acceleration. Right? Examiner doesn't have to question you on direct question. They can twist the question around to test whether you understand how to apply your knowledge. Right? This force is the resultant force. Varies with time. D. What does terminal velocity depends on? Weight of the object, surface area of the object, density of the medium. Right? If the medium is denser, then you achieve terminal velocity very, very fast. Surface area, that means greater area exposed to the increase of frictional force. Does terminal velocity depends on height of the object? No, it's constant for a particular object. Height only determines whether it will reach terminal velocity. Okay. A parachutist jumps from an aircraft. Sometime later, the parachute opens. Figure 1.1 is a graph of the vertical speed of the parachutist plotted against time. State what happens at t equals to 20 seconds and t equals to 55 seconds. 20 seconds is here. 55 seconds is here. Right? This one is the speed start to increase. Then it reach terminal velocity. Right? So this one you open the parachute. So there's a resistive force. Right? So in this part, parachute opens or the speed drops from 50 to 5 meters per second. Right? This part it lands on the ground. Right? This is where the parachute is on. Describe the motion of a parachutist from 0 to 20 seconds. Right? You adjust the time that speed increases. Right? The slope decreases, the acceleration decreases at about 15 seconds there. Acceleration decreases to 0 and the speed is constant. Speed or velocity or speed is constant. Parachute open at 20 seconds. Explain in terms of forces acting why the speed of the parachutist is constant between 25 is here, 5 and 55 seconds. Right? Air weight equals air resistance, thus no resultant force acting. So that's why it's moving at constant speed. Calculate the distance traveled by the parachutist. Distance is equals to area under the graph, speed time graph, that area, or area rectangle. Right? That is 5. That's 55 minus 25. Calculate out 150 meters. A sphere is released and falls. Its initial acceleration reduces until it eventually begins to travel at a constant terminal velocity, which displacement time graph best represent the motion of the sphere. So what's your answer? Right? At terminal velocity, the graph is a straight line. Right? Here don't have any part straight line. This part is straight line, that's not. So this is velocity time graph. Right? Displacement time graph, remember, no air resistance, it's a parabola. Going to go that way. Right? So there is a straight line. Answer is donkey. D. Okay, that's June 203, June 203, June. A ball falls from rest to air and eventually reaches terminal velocity. For these four forces X and Y varies with time as shown. So what is force X? What is force Y? What are the forces acting? The weight, friction, or drag? A. Force X is air resistance. Air resistance is proportional to velocity. So it's the same as, shape is the same as velocity. Right? Air resistance increases with time as the speed of the ball increases. Resultant force, that's your force Y, decreases as air resistance increases and becomes 0 at terminal velocity. It's almost 0 already. Okay, we'll go at this one. A sphere falls from rest through air. The graph shows a variation with time of the sphere's velocity. Which diagram shows the forces acting on the sphere when it is at the velocity that corresponds to P on the graph? Remember, your air resistance equals to the weight, then it will be terminal velocity there, somewhere around here. Right? This part is where somewhere around here, where velocity is almost 0. So this part, air resistance is significant, not equal to the weight yet. Air resistance is not negligible. At P, before terminal velocity, the weight is greater than the air resistance. So air resistance cannot be greater than the weight. That's important. So the answer cannot be donkey, cannot be D. The answer is C. Okay, have a go. This is 2013 June paper part 2. A skydiver falls vertically from a stationary balloon. She leaves the balloon at time t equals to 0. At time t equals to t, she reaches terminal velocity. Beyond the time shown in the graph, she opens a parachute. Which graph shows a variation with time t of the force due to air resistance? Right? Balloon stationary, so that means that she leaves the balloon at time t equals 0 at 0 velocity. So what is your answer? For small speed, the air resistance is very small. As the speed increases, the air resistance increases as your F is proportional to V. At terminal velocity, the air resistance is maximum. So answer is B. You are told that she leaves the balloon at time t equals 0. That's where it leaves the balloon. At time t equals to t, she reaches terminal velocity. Beyond the time shown in the graph, she opens her parachute. Which graph represents the variation with time t of the force due to air resistance? So we are looking at the force due to air resistance. So when you reach terminal velocity, air resistance, which is this force, reaches its maximum value already. It cannot go any further. It's going to be constant. Okay, so you just follow the velocity time graph, air resistance. Then after that, constant. Okay, that's the end of the lesson. We'll see you in the next topic, which is conservation of linear momentum.